Hello, yes, it's time for some waves practice questions. So we got here figure 4.1 shows a section of a uniform string under tension at one instant of time, right? So it needs to be under tension in order to transfer the wave. You know, you can't play a guitar with slack strings. Progressive wave of wavelength 80 centimeters. All right, so let's put that down. Moving along the string from left to right. So it's moving that way. At the instant shown, the displacement of the string is 0 at the point opposite the 0 mark on the scale beneath the string. Right, convoluted way of saying that this O here is at equilibrium, you know, next to the 0 on the scale. So, yeah, anyway, that's what it's getting at. 4 points P, Q, R, and S at those positions, respectively marked on the string, P, Q, R, S, yep. The motion of each point can be described in terms of amplitude, frequency, and phase difference from O. So state the meaning of each of these terms. So yeah, starting off with some definitions then. So let's then go with amplitude first. So amplitude, that is the maximum displacement from the equilibrium position of an oscillator on an oscillating point. Oscillating, nearly spelt that wrong. Maximum displacement of an oscillating point from the equilibrium position. I'll just do a shorthand for equilibrium there. Obviously, you'd write that out in full. Maximum displacement of oscillating point from the equilibrium position. Right, frequency is that's our number of oscillations per unit time. Number of oscillations per unit time. I mean, you'd probably be able to say per second. I don't think they'd have a problem with that, but per unit time, number of oscillations per unit time. Again, you might even want to say at a point on the wave. Point on the wave. You don't necessarily need that bit, I don't think, at the end. And then we've got our phase difference. Right, this is the one that people normally have more trouble actually saying what it is, actually describing it. It's one of those ones you really want to prep in advance. Now, they're quite happy with the description of how far out of step. They're quite content with that on mark schemes usually, or at least all the ones I've ever seen. How far out of step the oscillations are, but you need to mention at 2 points on the wave, because we're a phase difference. If you're going to have a difference, you need to have 2 points to have a difference between. So you want to say at 2 points on the wave. You know, if you remember with phase difference, this is where we've got what we're modeling as a simple harmonic oscillator, these things going up and down. But remember, with our simple harmonic motion, you can relate that to circular motion, and we can describe this variable speed simple harmonic up and down motion. We can describe that in terms of a constant speed circular motion, and we can then split that circular motion up into angle and talk about going through 2 pi of phase. So we can say, well, how far, if we're talking about how far through an oscillation one point is compared to another point, we can say how far how much the angles are differing. If we're at the top on one of them, then we're at pi by 2. If we're then at the bottom, we're at 3 pi by 2, and they'd have a difference of pi in the phase. So that's what we're doing with phase. Which I've gone through that in more detail in another video, but just a quick reminder there. Right, so that's done that bit. Describe using these 3 terms how the motion of points P, Q, R, and S are similar and different. So they're gonna, well, we need the same terms. They're all going to have the same amplitude and they're going to have the same frequency. So that's going to be amplitude and frequency are the same, but the phase is going to change, and the phase difference is going to change as we go along the string. So they particularly want phase difference rather than phase. So the phase difference, how the motion of points, P, Q, R, and S, right? They're all in the same wavelength. So we can say the phase difference is different for P, Q, R, and S. it would start to repeat. I mean, again, depending on how you want to talk about phase difference, but usually people would think, you know, our wavelength is ending there. Say we went another 10 centimeters, so like P dash. So this is the equivalent of P in exactly the same place on the next wavelength. Then you'd say, well, that's got the same phase difference with O as P does. So, you know, but if they're all in the same wavelength at different points, then they're all going to have different phase differences compared to O. So we're quite safe putting that down as a difference between the two of them. But I think this question went on to the next page. Yeah, it does. Figure 4.2 shows the same section of string now held under tension between a clamp and a pulley, 80 centimeters apart. A mechanical oscillator is attached to the string close to the clamped end. Frequency of the mechanical oscillator is varied until the stationary wave shown is set up. Right, okay. And then we've got the same point. So this is the oscillator. All the oscillator is doing, you know, you start off with a level string, is just completely flat, and then the oscillator just starts going up and down. It's just pushing the string up and down and making a wave appear. It's like plucking the string of a guitar. You know, your fingers doing the same thing. Describe how a stationary wave is different from a progressive wave. Right, progressive waves, so they will transfer energy or information. So progressive waves transfer energy. I mean, energy would be enough. You'd have to say both, but you know, sometimes we talk about waves transferring information rather than just energy. Whereas a stationary wave, you need to do the contrast here because they're asking you how is it specifically different. You can't just say, oh yeah, progressive wave transfers energy. You need to say, I know it might seem obvious, but stationary waves, well, they don't. They trap energy. But you need to actually put that contrast in rather than just making a statement about a progressive wave. Explain how the stationary wave is formed on this string. So it's another one of these process things that we need to talk about. So we can say, you know, imagine it as a bullet list. Just don't bother putting the bullets on. So wave propagates towards fixed end of string. Again, I'll just write this out in sort of shorthand. Wave reflects from fixed end. So yeah, you're just going through step by step. Then you can say the reflected wave will superimpose or superposes with incident wave. So again, another good term to use, incident wave. You know, have that word in your dictionary, in your vocabulary that you can use, and then say, you know, this produces a resultant wave. So again, another good technical term to use. And then we can say that's got with nodes, antinodes, so more technical terminology, and no energy transfer. I mean, you're really covering all bases then if you're mentioning all these different things. But it's that step-by-step thing. Just think what's happening as we go through time. Wave propagates, wave reflects, wave superposes, produces resultant wave. So that's good. Describe using the terms amplitude, frequency, and phase difference how the motions. All right, so we're doing the same sort of thing again going on this. But remember, with stationary waves, things are behaving differently. Like if you're in this same section here between two nodes, then P and Q are going to be in phase. And in this case, they're both, what are they? Both 10 centimeters from a node. So they're also going to have the same amplitude. So we can say P and Q have got same amplitude and same phase. So again, write out amplitude and phase rather than the symbols. And then with S is going to be, well, it's got a different amplitude, and it's going to be pi out of phase with P and Q. is going to be doing exactly the opposite. If P and Q are going up, S is going down. So that's what we've got there. I mean, I suppose you could say it's got a larger amplitude rather than a different amplitude. I mean, it's, swings and roundabouts really on that sort of thing. You could describe that as being anti-phase, I think is another term that people use for that. But there you go. It's just so you can show that you know the difference between what's gone on previously when we had a progressive wave and what's going on now with the stationary wave, how things start. The phase difference isn't just propagating along the wave in the way that it was on the progressive wave. Now it's sort of trapped in everything in phase if you're between nodes. Right, last part. In figure 4.2, the frequency of oscillation is 30 Hertz. State with a reason the lowest frequency of oscillation of the string at which the motions of all P, Q, R, and S are in phase or all at rest. Right, so if they're all in phase, then we're going to need to have a node at either end, pretty much. Yeah, that's the only way we're going to set it up in order to have a stationary wave there. So we're going to have just it's just going to have to be a wave that's looking like that is going to be our stationary wave. So we are doubling the wavelength, which means we're going to have to halve the frequency because the velocity of the wave is going to be the same. So that means we're going to have 15 Hertz. If they're all going to be at rest, so we're going to need there to be, well, nodes every 10 centimeters then, because, yeah, that's what we're going to need, aren't we? Because it's the only way we're going to get a node at all of these points. We need nodes every 10 centimeters all the way along. So it's going to be doing this sort of thing, isn't it? So we would have changed to having, how many is that? That's now 4 wavelengths rather than 1 wavelength in there. So the wavelength now is a quarter of what it was before, which means our frequency will be 4 times higher, which means 120 Hertz. So all the stuff, if you ever get confused with all the things with standing waves and these stationary waves, it is all about just deciding where your nodes are. So when you're, like when we were going through harmonics, again, I've done this in another video, your first harmonic is, well, what's the quickest we can do? 2 nodes. Now let's go for 3 nodes. So we'll stick one in the middle, and now we'll join those up. And then we'll just keep on adding nodes in. We'll now do another node. How many have I done there? Right, so you can then do 4 nodes. There you go, and you just keep building them up. You just keep adding another node in every time, and you keep seeing what's happened with the wavelength. Sometimes they put little restrictions on. You see some questions where they say, oh, you always have to have a node in the middle or something like that. But yeah, we're just building them up that way, and that's all we're doing here. We say, well, if they're all at rest, they've all got to be at nodes. So it's just marking where the nodes are. So you've got to have node every 10 centimeters, and then, well, there's only 1 line you can draw in. Well, I suppose there's 2 lines you could draw in. You could have the wave going upwards at first, or you could have it going downwards, but it's the same thing. You're just drawing the envelope in. Sometimes they draw in both lines. You'll get one which is drawn with a solid line and one that's drawn with a dotted line. That's just showing the envelope of what the standing wave is doing. It's like the solid line is, well, here's an instant in time, and the dotted line is, well, that's where it can end up, sort of thing. One extreme to the other. So anyway, that's a really nice question to start off with. Actually, you covered loads of terminology, a few calculations, bit of recap on what's happening with things like phase and these stationary waves. So yeah, good starter there. All right, next up we've got another meaty looking question. Figure 5.1 shows 2 loudspeakers S and T connected to a signal generator. Okay, so ST, yeah. Emitting sound of a single frequency with different amplitudes. Person walks in the direction O to Q, so they're walking up here. The line OQ is a distance D, yeah, from the loudspeakers. Right, okay. The sound waves emitted individually by S and T have displacements XS and XT at the point P. figure 5.2 shows the variation with time. Right, okay. All right, so they've given us these two. So T is louder than S. It's got a double the amplitude. And we'll see that they are anti-phase from each other. We've got a pi phase difference between the two of them. And as in, we got a peak here where we got a trough there, and so on all the way through. So what's happening then? Explain whether or not the two waves are coherent. Right, okay, well, there's two different ways of answering that. There's the A-level exam question answer, which is yes, because they've got a constant phase difference. So that's what you'd want to put in this. If you want a more sophisticated discussion of whether waves are coherent or not, go and watch my video on coherent waves. But that's what they want here. We're only considering phase difference when we're talking about coherence in an A-level exam. Explain why the sound heard at P will be of minimum but not zero intensity. Right, where am I actually going to write all of this down? So let's put it up the top. So it will be minimum because they are in anti-phase. So, or you could say they got a pi phase difference, but there's still a resultant amplitude. Oh dear, put about 4 L's in still there. Still a resultant amplitude because the amplitude of the individual waves are different. So I can't fit all that in, but still, because yeah, amplitudes are different. There's a difference between the two of them. So that's why we're not going to get a minimum. You know, normally when we are going to get a minimum, I mean, but it's not going to be zero. Normally when we're doing these things, they give us two identical sources. So by the time we've moved out to P and they're in anti-phase and they've got exactly the same amplitude, then they completely cancel out with each other. Whereas here, yeah, we've got a 2 and we've got a 4, so they're not going to completely cancel out. So we're just going to get a minimum, but no zero. State the phase difference between the oscillation at time A. Where's time A labeled on the t-axis of the? All right, here we go. Oh, A here, and against T, yeah, and the oscillation at time B and time C. Right, so we want phase differences here. Right, so we can split up our wavelength into 2 pi. So we've got a wavelength there going from 0 to 0.8, which seems to be a oh, well, that's not a wavelength, that's a period of oscillation. This is in time, of course, not distance. So, but that's still identifying one oscillation of the wave. So it doesn't matter if you're looking at one oscillation in terms of time or one oscillation in terms of distance. We've still got one oscillation that we're splitting up over 2 pi's worth of phase. So we can sit that at 2 pi. B then is going to be at pi. A is going to be at pi over 2. And C is going to be, where are we? That's going to be pi and a quarter. So 5 pi over 4. So we now just need the differences between these. So the difference between B and A, so pi minus pi over 2 is equal to pi over 2. And then for C, we've got 5 pi over 4 minus pi over 2, which is 3 pi over 4. Okay, so yeah, that's the way you always want to think about your phase differences when you're working those out. Calculate the wavelength of the sound waves emitted from the loudspeakers. That's our speed of sound. Right, well, we've got our usual, well, we know that the speed is the frequency times the wavelength. We know the frequency is 1 over the time period. So we want then that the wavelength is going to be the velocity of the wave, the speed of the wave, multiplied by the period. So that is 340 multiplied by, we got 0.8, and remember this is in milliseconds, which is an easy one to miss because they haven't mentioned it in the text. It's only there on the label of the axis. So we need to multiply that by, what did I say, 0.8, so 8 times 10 to the minus 4. That's going to be our wavelength. I mean, remember these are, I think they said they were micro, oh no, they just said, didn't say microwaves on this. Oh no, they're just sound waves, of course, yeah, what we're talking about. We're in sound, not electromagnetic. So we've got there, I mean, you could stick this into the calculator, couldn't you? Would probably be an easy way to do it, but we're going to have, well, 34 times 8 is 272. So we'd have 272 times 10 to the minus 3, so 0.272 meters. There we go. So that was easy enough. Right, the maximum intensity of sound is heard at point O. Yep, as it would be. Yeah, you're going to be in phase there, so we're going to get some constructive interference. Loudspeakers are 0.4 meters apart. Yeah, OP is 2.4 meters. Yeah, they put all that on the picture. P is the position of the first minimum. That is important. Calculate the distance D. Assume that the equation used for the interference of light from a double slit also applies to this. Yeah, so we can use, I mean, it's in the formula booklet, but you do this quite a lot. AX over D for the wavelength. Obviously, you're going to want to rearrange that in order to work out what D is. The importance of saying this, the first minimum, is remember that this X is the distance between the fringes. So difference between two maxima or two minima or something like that. So if this is then going from a maximum at O to a minimum at P, that means that our X is going to be double that. It's going to be 4.8 meters. That's going to be going between two minima or two maxima. That's what we're getting there, distance between fringes, if you were thinking of double slit with light interference. So this means that D is going to be our A, which is 0.4, multiplied by X, which is 4.8, and then divided by our wavelength, which is 0.272. And this time I definitely will be going to the calculator and getting 7.1 meters for D, which sounds quite plausible. So I'm happy enough with that. E, explain the term intensity. So, right, again, it's always the kicker you have to put in at the end of these sort of things, because a lot of people just say, oh yeah, it's power per unit area. Well, okay, it is power per unit area, but don't leave out the perpendicular to direction of energy transfer, because that's really what we want, energy transfer. You know, it's no good just saying, you know, we've got some surface that the power is going through, but it's going through at an angle. We need this to be perpendicular. You've either got to take a component of the surface or a component of the energy transfer. So yeah, make sure you've got all that in there. Power per unit area perpendicular to direction of energy transfer. So that's our straight definition there. You know, draw up a list, or write up a list, more to the point, of your definitions on all these things. You know, you only take up one side of A4, but you'll have the whole lot down. You know, in waves, you can have amplitude, frequency, phase difference, coherent, intensity, all these things. Just write down one sentence for each one of them, just so you make sure that you don't forget all of these little bits that you want to add on to the end of them to make your definitions precise. Right, the last part, the intensity of the sound at point P, the minimum, is 4 times 10 to the minus 6 watts per meter squared. Use data from the graphs to calculate maximum. Right, so at a minimum, we were already saying that we've got this resultant amplitude, because they don't have the same amplitude. Even though they're out of phase, they're not going to completely destroy down to nothing. So when they're combining for a minimum, we're getting, say, a 4 from the big wave, from the loud one, and we're going to get a -2 from the other one, because that's just combining these amplitudes. I know it's in micrometers, but yeah, we're looking at proportional, relative difference here. So we've got a 4 and a -2, but if we're at O, they're now going to be in phase. So we're going to have a 4 plus a 2. So we're going from a 2 to a 6. That is going to be our ratio of the amplitude, resultant amplitude at P to O. That's going to be our ratios there. Now we know that the intensity is proportional to the amplitude squared. So we're going from 2 to 6. So we're doing 3 times the amplitude. We're going to do 9 times the intensity. So amplitude times 3, therefore intensity times 9, which means we're going to have 36, so 3.6 times 10 to the minus 5 watts per meter squared. So yeah, yeah, providing you keep that. I mean, most people are usually happy with the intensity proportional to the square of amplitude. So yeah, nice little calculation to finish off. That's two really nice questions. So a lot of detail in both of those, lots of bits covering a lot of ground. So I'll leave it on those two because this has already turned into quite a long video. So yeah, there you go. First two questions.